ओके, चलिए स्टार्ट करते हैं। अच्छा, देखें स्कैटरिंग थ्योरी। वी वर डूइंग स्कैटरिंग थ्योरी लास्ट टाइम। और when you when you sort of perform scattering experiment, then there are certain number of parameters which are involved, and those parameters need to be understood in order to know the target particle or the incident particle and how they collide with each other, and what information we can obtain from such a collision process. Then, furthermore, not every collision of a microparticle of microparticles that has to be treated using quantum theory. And in those cases where quantum theory is not to be used, classical theory may be a perfectly valid approach. दूसरा ये है कि the basic ideas of classical theory, they would translate into quantum regime. That is, in order to understand scattering theory quantum mechanically, one must have the understanding of scattering theory or collision theory in a classical sense. And once we have those that understanding, then we can translate that classical understanding into quantum regime. What today we will be doing, we will understand the concept of in and out asymptotes. In fact, we know we have a concept of asymptotes as something which have a long range value, but it is not zero. That is, there is no definite sharp cutoff region. And so, if there is no sharp cutoff region, then you could define that physical quantity as being geometrically as being some asymptote. So we would be discussing about in class using this classical theory of scattering, the in and out asymptotes. And these they would be translated into quantum theory as in and out asymptotic states of that system, where we have incoming particles coming from infinity, minus infinity, and then scatter from the target, and then scatter into plus infinity. So at minus infinity and at plus infinity, we would have in state and out state, and these in state and out state are termed as asymptotic states. So if the potential is a long range potential, for a short range potential, the physical quantities, they have a sharp cutoff region, would not give you an asymptote, but for a long range potential, there would be an asymptotic behavior. So, from the classical understanding, we will have the concept of in and out asymptotes, and these they would be translated into asymptotic states, in state and out state, incoming particle and outgoing particles, corresponding to incoming and outgoing particles. And then, from the definition of scattering cross section, classical scattering cross section, we will have the quantum scattering cross section, and then those scattering cross sections would be related with theory, uh, from experiment to theory and from theory to experiment. So this would be our topic today. So in order to start the classical description of this, in fact, this scattering process, deflection function से start करेंगे. Deflection function से मुराद है that is a deflection of the incoming particle into outgoing beam of particles, and that deflection function would be some function of uh, impact parameter that you have learned in your classical mechanics course. हम यहाँ पर दोबारा से बात करेंगे impact parameter से क्या मुराद है हमारी, and some deflecting angle. Yeah. So let's start with the deflection function. And deflection function, we will assume, as previously, we will assume a simpler case, that is for a deflection function for a single particle. So let's start the deflection function. Uh, function for a single particle. So we assume अगेन उसी तरह से जैसे पहले हमने बात की, we assume that the particles they are moving in some spherically symmetric potential that is represented as V of R. So उसके कुछ advantages हैं when we say that the particles are moving in some spherically symmetric potential. We would have some advantage which are related to conservation laws. So we assume that the particle is moving in a spherically symmetric potential. Let's say we call it as V of R. And this potential can now जैसे मैं हमने बात की ना asymptotes की और asymptotic states की और otherwise, so we could think about the potential, जो potential हम यहाँ पर इस्तेमाल करें, again एक और assumption करें that the potential can be strictly short range. अगर वो short range होगी तो that would be exactly zero beyond a certain point. And if the potential is not short range, then it would form some sort of an asymptote. That is, हम potential जो जिस potential के अंदर particles are impinging on the target, that is basically the potential associated with the target, वो short range है या long range है. So that is also one of the assumptions. So the potential, जिस potential के अंदर particles would move, can be strictly short range. शॉर्ट रेंज का मतलब है दैट इज एग्जैक्टली जीरो beyond a certain radial distances, and that radial distance would be yeah, so that would be considered as impact parameter आगे चल के, certain radius or a long range potential, long range potential. And this long range potential which sort of goes smoothly to zero as R tends to infinity. So that is basically certain types of assumption. और इस तरह के सिस्टम को एक्सप्रेस करने के लिए लेट्स से हम एक ग्राफिकल रिप्रेजेंटेशन देते हैं. सो थिंक अबाउट दिस इज सम reference axis and we have the target. Yeah, so जिसको हम origin का नाम दे दें. And then we have a beam of particle or a single particle that is basically coming from this direction, and then it moves along and goes in this way. Yeah. So we would have this beam of particle with velocity v in this direction. Yeah. Then this distance, this perpendicular distance, perpendicular to the target, is denoted by b. इसको impact parameter कहा जाता है. Then we can make some triangle. Very difficult to make lines here. So we have some triangle with this angle, हम इसको phi कह दें, let's say. Yeah. And we can draw a perpendicular जिसको हम a से जाहिर कर दें, और perpendicular distance, और इस point को हम कोई अभी हम बात करेंगे. This is इनफैक्ट दिस लाइन जो ये आपके पास कर्व नजर आ रहा है, दिस इज इनफैक्ट द पार्टिकल ट्रिजेक्ट्री, पार्टिकल ट्रिजेक्ट्री x of t. Yeah, we have an incoming particle जिसको हम I x I n of t से जाहिर कर रहे हैं, and that is some a in, ये कोई initial displacement है, this is not acceleration, this is some initial displacement plus v I in into t, that is v, again v in is the initial velocity, and then output trajectory uh, o x of t, and this is again a out plus v out into t. So this is some particle, and then we could have so something like this. So this is theta, that is डिफ्लेक्शन एंगल, इसको हम नाम दे रहे हैं डिफ्लेक्शन एंगल। सो दिस इज द डिफ्लेक्शन एंगल जिसको हम निकालना चाहते हैं यहाँ पर, ठीक है ना। सो अगर हम इस फिगर के लिहाज से सोचें तो क्या क्या क्वांटिटीज हैं। वी हैव अ पार्टिकल विच इज कमिंग फ्रॉम द लेफ्ट, and this particle is basically characterized by two quantities. Number one, its velocity, and number two, b. इस b को हम क्या नाम देते हैं, impact parameter, which is a perpendicular distance of the beam from the target here. So एक जो बात है वो क्या है, number one, the particle impinging on the left, and that is characterized by its velocity v and impact parameter b. या एक बात, दूसरे नंबर टू, आफ्टर कोलिजन क्या हो जाएगा, द पार्टिकल दैट वुड बी लीविंग, it would be leaving along some line giving by some angle which is known as the deflection angle. So after the collision, the particle is leaving along some along some line, along a line uh, which is given by the deflection angle. So it means deflection angle theta. So it means that the incoming beam of particle, it is characterized by two parameters, velocity and impact parameter. The outgoing particle is characterized by a line, and that line is basically characterized by an angle which is known as the deflection angle. Then there is another very important point which is known as the point of closest approach. The point of closest approach is in fact this quantity, and this point of closest approach is a point which is characterized by saying that the radial velocity is zero. So there is no more radial velocity at this point, and then when it leaves this point, then its radial velocity changes. So this is the point of closest approach. So number three, the point of closest approach is the point where the radial velocity, is zero. That is dr upon dt is zero. R, if r is the radius for this particle which is moving in some sort of some kind of a curve, then the radial velocity is zero. And you see this quantity here in this figure. Okay. Then the corresponding distance from this, in fact, uh, the corresponding distance, the corresponding distance of the point of closest approach to target is A. इसको हमने फिगर में ए से जाहिर किया हुआ है. सो दीज आर द क्वांटिटीज जिनको हम यानी दूसरे लफ्जों में दीज आर द क्वांटिटीज जिनको हम यहाँ डिस्क्राइब कर रहे हैं फॉर दिस फिगर. ओके. ओके. नाउ दूसरी चीज ये कि जो इनफैक्ट पार्टिकल है, दैट इज द करेक्टर अदर करेक्टराइजिंग फीचर ऑफ द पार्टिकल वुड बी इट्स एनर्जी. सो द एनर्जी ऑफ दिस इनकमिंग पार्टिकल, it has to be conserved. Conserved का मतलब है that the total energy, for example, इस केस में we start with a very simple idea of elastic collision. So the energy of the incoming particle is conserved. एंड दूसरी बात, ड्यू टू स्फेरिकल सिमेट्री उसका एंगुलर मोमेंटम भी कंजर्व होगा. ठीक है ना. सो हमने नोएडा थ्योरम से ये चीज़ दोनों चीज़ें बात करें तो नाउ वी हैव so energy of the incoming particle is conserved, and due to spherical symmetry, uh, its angular momentum, that is incoming beam का angular momentum is also conserved. So both are, in fact, both quantities are conserved. So because of this, it's a very important, in fact, the very important consequence of these two conservation, that the motion of the particle would be in some plane. That is, it would be constrained to move in a plane. Therefore, the motion uh, of the particle is constrained to a plane. So it is basically, this is the consequence of these two conservation, that if the energy of the particle is conserved and due to spherical symmetry, its angular momentum is also conserved, then the motion of the particle is constrained to be in a plane, and that is one of the simplicity. And now the particle has some fixed energy and angular momentum. So क्योंकि ये दोनों कंजर्व है, तो दोनों के लिए हम फिक्स एनर्जी और मोमेंटम डिफाइन कर सकते हैं. Therefore the particle now has fixed energy and angular momentum. And that is, in fact, E is equals to half mv square. This को equation number 1 कह दें, और L is equals to पोलर कोऑर्डिनेट में लिखते हैं m r स्क्वायर ओमेगा, और ओमेगा किसके बराबर होता है, डी फाइव बाई डी टी. सो दिस इज डी फाइव अपॉन डी टी विच इज इक्वल्स टू एम वी आर के बराबर होता है. और एम वी आर यहाँ पर आर किसके बराबर है, बी इम्पैक्ट पैरामीटर जो कर्व का रेडियस है. सो एंगुलर मोमेंटम एल जो होगा दैट वुड बी एम आर स्क्वायर डी फाइव बाई डी टी, और एल इज इक्वल्स टू एम वी आर के बराबर यानी एम वी बी. दिस इज इक्वेशन नंबर 2. या सो यहाँ पर क्या क्या चीज़ें, so we can say where where phi जो है that is some polar angle, या b impact parameter, इसकी भी वैल्यू हम निकालेंगे, पैरामीटर। एंड तीसरी बात, फाई इज द, फाई इनफैक्ट जिसको आप पोलर एंगल कह रहे हैं, दैट इज सम, इस एंगल का नाम हम दे रहे हैं डिफ्लेक्शन एंगल, नॉट फाई, सॉरी, डिफ्लेक्शन एंगल, फाई नहीं, थीटा है। तो थीटा इज द डिफ्लेक्शन एंगल, क्या, जो उस फिगर के हिसाब से हॉरिजेंटल एक्सिस जो पार्टिकल का बना है दैट इज बेसिकली पैरेलल टू दी, ये इनिशियल हम सारी फिगर को ड्रॉ कर रहे हैं कि हमारा एक्सपेरिमेंटल सेटअप क्या है, या जिस एक्सपेरिमेंटल सेटअप से हम थियोरेटिकल अंडरस्टैंडिंग निकालना चाह रहे हैं या थियोरेटिकल कैलकुलेशन करना चाह रहे हैं, उसके अंदर the horizontal axis जो है that would represent the particle velocity, magnitude of angular momentum ये आप निकाल सकते हैं, अगर आप इनफैक्ट ट्राइंगल को सॉल्व करें, कौन से ट्राइंगल को, जो लो ट्राइंगल हमने उस फिगर के अंदर देख रहे हैं जहाँ पर द एंगल इज फाइव, या सो इनफैक्ट दूसरी चीज, हॉरिजॉन्टल एक्सिस इज पैरेलल टू पार्टिकल वेलोसिटी, एक बात। दूसरी चीज ये कि द मैग्नीट्यूड ऑफ एंगुलर मोमेंटम is obtained by is obtained by solving the lower triangle in the figure above, in the above, and that is basically rp sin theta, which is equals to किसके बराबर होता है, m v b, b is the perpendicular which is in fact your, uh, so again वो sin theta is perpendicular upon base, and or sin phi इस केस में. Okay, now the trajectory of the incoming particles, it is basically specified by two parameters, the A in, which is the displacement of the particle, and V in, which is the velocity of the incoming particle. So the trajectory of the incoming particle is specified by a pair of vectors, and what is that pair? That pair of vector is A in, which is, and V in, and what these two pair of vectors correspond to, they correspond to displacement and in fact velocity of the incoming particle. So these two in fact parameters, they would characterize the incoming particle which has displacement a in and velocity v in, corresponding to the particle's displacement, is displacement and velocity, sort of respectively. Yeah. Similarly, after scattering, so these are after scattering or after collision, the outgoing uh, particle which is found found on a detector and is characterized by again two parameters. कौन कौन से? A out or V out. That is uh, again which is that is the displacement of the outgoing particle and the velocity of the outgoing particle. Now we can expect that any pair of vectors A and V can define in and out asymptote. So you can think about these two pairs, that is ये pair, that is so this pair and this pair, they can be considered as an in asymptote and the out asymptote. Yeah, so if they are in asymptote and out asymptote, then you can expect, जैसे मैंने आपसे कहा ना, experimentally there are lots of particles which are coming towards the target particle, or the two beams are interacting with each other. Then इसका मतलब हो गया कि we can expect any pair of vectors A and V that can define an in and out trajectories or asymptotes. So it is expected that any pair of vectors meaning A और V, ख्याल रखिएगा ये ए एक्सेलरेशन नहीं है, बल्कि हम यहाँ पर डिस्प्लेसमेंट कह रहे हैं, ठीक है ना, डिस्प्लेसमेंट ऑफ द बीम ऑफ पार्टिकल्स इन बीम एंड इनकमिंग बीम एंड आउटगोइंग बीम can be defined can define in and out asymptotes. Yeah. So these are some of the characterizing feature. Now एक और बात जो बहुत इम्पोर्टेंट है यहाँ पर, जो ऑर्बिट है एक्स ऑफ टी, जरूरी नहीं है कि हर ऑर्बिट एक्स ऑफ टी के इन हो और आउट एजम्प्टोड हो। किसी पार्टिकल का ऑर्बिट जो है वो सिर्फ इन एजम्प्टोड हो सकता है, आउट एजम्प्टोड नहीं हो सकता, और किसी केस में आउट एजम्प्टोड हो सकता है, इन एजम्प्टोड नहीं हो सकता। फॉर एग्जाम्पल, इफ देयर इज अ वेरी strong attractive potential, then the incoming beam of particle would be attracted by the target, and it is basically then it becomes a bound state of the system. That incoming beam of particle, or a single particle or a beam of particle, then become part of the target, and it then becomes some bound state of the total system. Then there would be in asymptote, but there would not be any out asymptote. Yeah. Similarly, ये भी हो सकता है कि particle is just like, for example, ionization. In case of ionization, a particle just come out of the atom, and there is no incoming beam of particle or in particle in asymptote, but there is an out asymptote in that particular case. So there could be an attractive potential and there could be a repulsive potential. In case of attractive potential, strong attractive potential, the orbit would have the in asymptote, whereas in case of a strong repulsive potential, the orbit of the particle would have just the out asymptote. Yeah. So, however, not every orbit x of t has uh, in and out asymptotes. meaning the potential can support bound states as well. यानी यानी दूसरे लफ्जों में, if there is a strong attractive potential, then there would be an in asymptote but no out state, and for the repulsive potential as out asymptote but no in asymptote. So in case of scattering experiment involving some microscopic particle or microparticle, we don't have the access to the exact orbit x of t, and we only observe the asymptotic states of the particle. So uh, that is very important, that when you perform experiment, you do not have actual orbit of the particle. What you can access only are the in asymptotes and out asymptotes. So in any scattering experiment involving microscopic particles, one does not have have an access to the exact orbit x of t, and what we have, we only observe the asymptotic states of the particle. Okay, so this is what we have in some actual experiment. And this is basically justified by previous equations जो हमने लिखी थी पीछे, सेकेंड इक्वेशन इनफैक्ट, जिसमें हमने कहा था कि L बराबर है किसके, एम आर स्क्वायर डी फाई बाई डी टी, दैट इज L इज इक्वल टू किसके बराबर, एम वी बी के. सो जो रेट ऑफ चेंज उस सेकेंड इक्वेशन के अंदर जो हम देख रहे हैं डी फाई बाई डी टी, दैट इज बेसिकली द रेट ऑफ चेंज ऑफ फाई, that is inversely proportional to the radial distance, that is जहाँ पर हमने लिखा हुआ है r. Yeah, so m r square into d phi by dt किसके बराबर था, m v r के बराबर. So one could say that d phi by dt अगर मैं निकालूं, that is the rate of change of phi, then we would see that it is inversely proportional to the radial distance of the particle. So the angle phi uh, is well defined when the particle is very far away from the origin. Very well defined का मतलब phi is equals to 0, and after collision phi is not well defined, so phi is not equals to 0. So जो हम ये कह रहे हैं ना कि in any experiment involving microscopic particles, we do not have this luxury of exact orbit, we only observe the asymptotic states. ये किससे justify हो रही है statement, equation number 2 से. और why? Because in equation number 2 we have d phi by dt, which is basically the rate of change of phi, and that rate of change of phi is inversely proportional to the radius, that is the distance from the target, which is some radial distance. And so it means that at very far away, before collision phi would be 0, so it is well defined, and after collision the phi is not well defined, because in that case phi is not equals to 0. So that would be the case where the particle, in fact, phi is not defined. And this justifies our statement that we do not have access to particle orbit. What we have access to is just the asymptotic states, which are in state and out state. Yeah, so एक दो सेकंड रह गए, 10 सेकंड रह गए, हम दोबारा से कंटिन्यू करते हैं, दोबारा ऑनलाइन हो, ठीक है. ओके.